Welcome to lecture 31 of Power System Protection course. In the last lecture, that is lecture 30, we discussed about the importance of sampling and hold circuit, and also we talked about the concept of anti-aliasing and the importance of anti-aliasing filter, because practical signal in the power system, in fact whatever the current and voltage signal we collect from the field, in fact it is consisting of many other high frequency signals. So therefore it is very important to remove those high frequency signals in order to avoid the anti-aliasing effect. So therefore these anti-aliasing filters are nothing but they are the low pass filters which plays very important role in removing the high frequency noises from the signals, from current and voltage signals. So also we talked about the design of anti-aliasing filter, that is the Butterworth type low pass anti-aliasing filter, and in detail with an example we illustrated how we can design. So in this lecture we'll talk about different algorithms to extract the phasor information from the sample values. So we'll talk about few algorithms, how we can implement these algorithms in numerical relays. Okay, so let us start with, we'll start with the algorithms based on the undistorted single frequency sine wave. That means here we will not consider the noises into account, because when the noise will be coming into picture we cannot get a undistorted single frequency sine wave. So here the assumption made is that we have a undistorted single frequency sine wave, and from that we can extract the information. So this is the algorithm. So first algorithm we are going to discuss is Mann and Morrison algorithm. So in fact this is not the first algorithm for the numerical relay. Before this also there are many other algorithms developed, like if I can say that the first algorithm was developed by Murthy, Professor M. Murthy, and it was published in the SIGRE journal. It was the first algorithm for numerical relay. So this is in fact came in 80s, Mann and Morrison algorithm. So it is the derivation of the sample and derivative algorithm, right? So this is Mann and Morrison algorithm. So here it is assumed that the signal can be represented as a pure sinusoid, okay, pure sinusoidal, whose amplitude as well as frequency is constant. It remains constant during the period under consideration. So where the period for which we are taking the samples, for that it is assumed that the sinusoid, the amplitude and the frequency remains constant. So this is Mann Morrison algorithm. You can see here this is the voltage waveform from PT and this is the current waveform from CT. In fact they are not so ideal as shown, because we are considering here a undistorted sine wave, undistorted sine wave or signal, right? So therefore it is considered an ideal signal. Here the clock decides the sampling instants at the rising edge. Okay, so let's say it is rising edge, and delta t is your sampling period, right? So now we have here three samples. One is your Vk, other one is Vk plus 1 and Vk minus 1. So by using these three samples, how we can extract the phasor information, let us see it. Okay, so now let us consider this signal. The signal considered here is Vm sine omega t plus theta v. Okay, this is a voltage signal, therefore the phase angle is mentioned in theta v. So now at the time tk, if I'll write the instantaneous value, I can write, this is one of the sample, Vm sine omega tk plus theta v, right? Similarly, if I'll take the derivative of this equation, that is v dash tk, then I'll find omega vm cos of omega tk plus theta v, right? Okay. So now omega is the extra term coming in picture. Now if I'll square it, I'll just square these two terms. That means vtk square plus v dash tk square. Then what will happen? I will just omega take this omega to this side, so it will become, it will take to this side, it will be divided by v dash tk. So now just by taking the square of both the side, I will get Vm square will be equal to Vtk square plus V dash Tk by omega square whole square, right? So from this equation I will get the amplitude of the voltage, right? That is Vm equal to Vtk square plus V dash Tk by omega square root. In fact, where some assumption is there, in fact here the assumption is the frequency is known here, okay, the omega is known and the unknown quantities are Vm and theta v. In fact, we need this Vm and theta v. This is in fact gives the phasor information, right? So from this I can find the phasor, because a phasor is consisting of RMS value. So Vrms is Vm by root 2. If I know Vm, the value of Vm, I can find RMS, and theta v obviously it will give the phase angle of the phasor, right? So now similarly for current, if I will write the current as instantaneous equation, I will write Im sine omega tk plus theta I, and that will lead to, if I will take the derivative, I dash tk will be equal to omega Im cos omega tk plus theta I, and from this equation I can find Im similarly in the way I have found Vm, right? I can find also Im, right? So Im will, the expression for Im will be I tk square plus I dash tk by omega square root. So for current and voltage both, we got the expression for the maximum value, that is the amplitude of the current and voltage signal, right? Now our objective is to find the phase angle. So therefore just by dividing these two equations, right, so I will find tan of omega tk plus theta v will be equal to v tk by v dash tk by omega. So from this equation I will find theta v just by taking inverse, tan inverse of this v tk by v dash tk by omega minus omega tk. So this will give me the information of theta v. Similarly, I can find the expression for theta I from the equation, current equation, and theta I will be nothing but tan inverse I tk by I dash tk by omega minus omega tk, right? This is a similar expression for voltage phase angle and the current phase angle, and also the magnitude, voltage magnitude and current magnitude, right? They are all similar. So now the question is how to find these derivatives. So the derivative of voltage and current signal, right? So that sample, so derivatives can be computed numerically using the central difference formula. Central difference formula we know, that is, if we know the sample values of Vk plus 1 and Vk minus 1, so I can write the voltage samples of Vk at the k plus 1th instant and at the k minus 1th instant, and the time interval between that. Time interval between these two instants is 2 delta t. So I can write Bk dash will be equal to Vk, that is the derivative sample, will be Bk plus 1 minus Vk minus 1 by twice of delta t. So if I know these samples, that like Vk plus 1 and Vk minus 1, right? So then easily I can find this Vk dash, and then after knowing this I can substitute Vk and Vk dash, right, or Vk dash or V dash Tk, right? Just substituting in these equations, I can find the magnitude of voltage, current, and the phase angle of voltage and current respectively. So similarly, Ik dash also I can find from these samples, Ik plus 1 minus Ik minus 1 by twice of delta t. Okay. So in this way, this gives us, this is the Mann Morrison algorithm. So if we'll summarize this, so our voltage signal, the model of the voltage signal is this, it is undistorted sinusoidal signal, and the model of current signal is this Im sine of omega tk plus theta I. And if we'll write from the above derivations, we can write the equations for Vm theta v, and Im and theta I, right? So Vm is nothing but Vtk square plus V dash Tk by omega square root, whereas we know Vk dash is this, right, already using the central difference theorem, and theta v is equal to tan inverse of this Vtk by V dash Tk by omega minus omega Tk radian. Similarly, Im is similarly defined Itk square plus I dash Tk by omega square root, and Ik dash is, this Ik dash is nothing but this is equal to I dash Tk, right, at the kth instant what is the derivative, right. So that is Ik plus 1 minus Ik minus 1 by twice of delta t. Similarly, theta I, expression for theta I is tan inverse Itk by I dash Tk by omega, right. So already we know I dash k, that is equal to I dash Tk. Okay. So now we this is the summary of Mann Morrison algorithm. Now it can be observed that the computation of one derivative requires 3 samples. This is very important, right? Now we cannot make the trip decision on a single estimate. It seems that we can do it with single estimate, but it is not possible because for calculating the derivative quantity we need 3 samples at least. So we have to continuously keep estimating the peak and the phase angle, and hence the phasor. Okay, when we know the peak and phase angle, we know the phasor in order to be sure about what way the phasor is really going. So thus the trip decision can be made on a sufficiently large number of estimates rather than a single estimate. So because in order to avoid the effect of noise, so we need to estimate more number of times, and when for many number of times it goes beyond the threshold value, then we can say that some fault is happening, right. So that is what this will make the decision more robust and provide some measure of noise immunity. Okay, so it depends upon how much noise is present at particular location. Based on that, the threshold is decided. So let us see the application or implementation of this Mann Morrison algorithm in an instantaneous overcurrent relay. Though it can also be used in the directional overcurrent relay. Let us see first overcurrent relay, and similarly it can also be used for directional overcurrent relay, right. So it is possible to implement a variety of relays based on Mann and Morrison algorithm, an overcurrent relay, directional overcurrent relay, right, or a distance relay, because when we extract the information like the magnitude and the phase angle, from that we get the information of phasor. Then we know, when we know the phasor information of voltage and current, that is only required for overcurrent relay, directional overcurrent relay, and a distance relay. So then we can easily implement this. So every relay requires first to compute from the instantaneous values of the input quantities the phasor for the input quantity. So this is important. So when we know we collect the samples from the instantaneous values of the signal, then from those samples if we can estimate the phasor, That is important. When we know the phasor input quantity, then easily we can implement the relay. So 3 samples will make one estimate of the phasor, right? So afterwards, one occurrence of every new incoming sample, we can modify our estimate by shifting in the newest sample. So it will gradually shift. The oldest sample will first removed, then a new sample will be entered. And when the new sample will enter, again the calculation will be made. And again the old sample will be removed and the new sample will be entered. Then again new calculation will be made. So this is called by shifting in the newest sample and shifting out the oldest sample, the estimate is being made. Thus we have a calculation window, right, of 3 samples which keeps sliding over the signal, okay, which keeps sliding over the signal. Then in practice we will not issue a trip signal as soon as the RMS value is more than the pickup value, because the increase in the RMS value could in all probability be due to the noise spike. So therefore it is not that with a single estimate we give the trip signal. Suppose we get the value greater than the pickup value, pickup current, it is not that we should give the trip signal. No, because it may be due to the noise spike. So therefore we need to hold it for some more number of times it should incur, right? So in order to avoid maloperation, we set up a fault counter and increment it every time the RMS value is more than the threshold, and decrement it if the RMS value is less than the threshold. So this is in case the counter crosses the predetermined threshold, we can be sure that there indeed a fault in the system and issue a trip command to the circuit breaker. So therefore this predetermined threshold it will depend upon the location where the measurement is being made. If at a location we have many power electronic devices, switching devices, right? So under that condition we should have an increased value of threshold, right? And when we have nothing, no switching device, nothing, like a simple transmission line system, then under that condition we don't require much threshold, right? So in that condition we can take a lesser value of threshold. So the threshold value to be used for the counter will be based on the severity of the noise at a particular location. That is what I told. Now we'll see, let us see how it can be implemented, right? You can see here, these are the current, this is overcurrent relay, therefore we consider the current samples, right? So here the current sample is this, right? Now the oldest sample is ik minus 1 and then ik plus 1, okay. So now these 3 samples are fed to some processor, right, where the Mann and Morrison algorithm is implemented, and we have a setting value, right, I per unit, I pickup, and then from this we calculate, from these samples we calculate the RMS value, right? As soon as the RMS value is checked with the pickup value, if it is greater than I pickup, right, then if it is S, then the counter increases 1, right, increment the counter. So when the counter is increased and again the count value is compared with the threshold value, right, when the count value is greater than threshold value, then then it will give the trip signal to the circuit breaker, right? If it is no, then obviously it will shift out the oldest value and a new value is entered, and hence with the newest value again it will calculate the RMS value. Again the RMS value will be compared with the pickup value. Then if it is S, then it will increase, like that. This cycle will continue till the count becomes greater than the threshold, right? When it becomes greater than threshold, then it gives the trip signal to the circuit breaker. So this is how the Mann and Morrison algorithm is being used for overcurrent relay. So this is for overcurrent relay, right? Overcurrent relay. Okay. So now, now let us consider the another algorithm which is also for undistorted signal, right? Considering or assuming the undistorted signal. This is the 3 sample technique. So what is the difference between this 3 sample technique and the Mann Morrison? The difference is that in Mann Morrison algorithm we assume that the frequency is known parameter, a known quantity, but here we are estimating the magnitude, the phase angle as well as the frequency. So frequency also is unknown here. So now we can see here 3 sample algorithm kind of extend of Mann and Morrison algorithm, but it removes the condition in Mann and Morrison algorithm that the frequency should be known, right? Here the frequency is also unknown, so we need to estimate the frequency. So here the signals, we can see the signal is V is equal to Vm sine of omega t plus theta, just substituting omega equal to 2 pi f, just we can write it as Vm sine 2 pi f t plus theta, right? So now also here we have 3 quantities to be estimated. One is your Vm, right? Then your f, then your theta. Theta is the phase angle, right? So now here we have t equal to 1 by f. This is the time period of the this voltage signal, and delta t is the sampling time period, that is 1 by f sampling, right? Okay, so this is your sampling period. Okay, now if we'll see, suppose because we have 3 unknowns, so we need obviously 3 samples. So I can write the 3 samples in the sampled form in the instantaneous values at particular instant. So let us consider the kth instance. So at a kth instance, if I'll write the equation, this will be Vk equal to A is the magnitude, that is the amplitude of the signal, A sine of 2 phi f k delta t. So instead of t I am writing k delta t because it is at the kth instant, so I can write k delta t plus theta. Similarly Vk plus 1 I can write it as k plus 1 into delta t. So k plus 1 into delta t will become 2 pi f k delta t plus delta t, right? Similarly for Vk plus 2 it will be A sine of 2 pi f k plus 2 delta t. So it is nothing but k delta t plus 2 delta t plus theta, right? So now we have 3 samples. From these 3 samples we need to estimate Vm, f and theta. So how we'll do it? Let us see. So first let us determine the frequency of the signal. Okay, now let us consider the summation of Vk and Vk plus 2. So this is Vk plus 2. So just by substituting the expressions of Vk and Vk plus 2 in this equation, we will get A times sine of 2 pi f k delta t plus theta plus sine of 2 pi f k delta t plus 2 delta t plus theta, right? So now if we consider x equal to 2 pi f k delta t plus theta and y equal to 2 pi f delta t, then I can write Vk plus 2, I can write it as Vk plus 2 can be written as A of sine x minus y plus sine of x plus y. Because if we'll write this from these x and y values, if we'll write x minus y, obviously I will get the expression of 2 pi f k delta t plus theta, right? Similarly, if we'll find x plus y, it will give us 2 pi f k delta t plus 2 delta t. So therefore instead of these instead of 2 pi f k delta t plus theta, I can write x minus y, and instead of 2 pi f k delta t plus 2 delta t, I can write x plus y, right? 2 delta t plus theta, right? Plus theta, sorry. So I can write it as x plus y. Okay. So now substituting these quantities, just I can write is that Vk plus 2, I can just just expanding these terms, I can find twice of sine x cos y, right? So just substituting x and y value, I will find twice of sine 2 pi f k delta t plus delta t plus theta into cos of twice f delta t, right? However, we know that a of sine 2 pi f k delta t plus theta, this is nothing but this is equal to bk plus 1, right? Now substituting bk plus 1 here in this equation, right? So we'll have only remaining term this, right? So now just substituting bk plus 1, we'll find bk plus 1 bk plus 2 equal to twice of bk plus 1 into cos of twice 2 pi f delta t. Now from this expression I can write cos 2 pi f delta t will be equal to vk plus 2 by twice of bk plus 1, and from this expression I can write 2 pi f delta t will be this cos inverse of vk plus 2 by twice of vk plus 1, and from this I can write f equal to 1 by 2 pi delta t cos inverse vk plus 2 by twice of vk plus 1. So now I found if we know the samples vk plus 2 and vk plus 1, I can estimate the frequency of the signal, right? Since delta t, the sampling time period, which is 1 by f sampling, is known, the unknown frequency can be estimated with the help of the 3 consecutive samples. Okay. So next is coming to how I can determine the amplitude of the signal. So the amplitude of the signal also can be determined in a similar fashion. Now in order to estimate the peak value A we have taken the peak value of the signal. So let us consider this equation, that is Vk plus 1 square minus Vk into Vk plus 2. Just evaluating this expression, what we will get? Finally we will get this expression if we will take common a square. So a square if we will take common, it will become sine of 2 pi f kt plus delta t plus theta whole square minus sine of 2 pi f k delta t plus theta sine of 2 pi f k delta t plus 2 delta t plus theta, right? Okay, now using the trigonometric identity that sine square theta is equal to 1 minus cos 2 theta by 2, just by substituting we'll get this expression sine of for this sine of 2 pi f k delta t plus theta square, I'll get 1 minus cos of 2 into 2 pi f k delta t plus theta by 2, and this will if we'll write that 2 pi f k delta t plus 2 delta t is plus theta is equal to x, then I can write it as 2 pi f and also 2 pi f k delta t plus theta equal to y, then hence we can write this expression, right, for this, right. For this I can write sine of 2 pi f k delta t plus theta into sine of 2 pi f k delta t plus 2 delta t plus theta. For in order to simplify this expression, I am just substituting the values of x and y, and after substituting and simplifying, I will write cos of x minus y minus, here it is cos of x minus y, right. This is your x, this is your y, right. This is your x, right, and this is your y. So I can write it cos of x minus y. So if I'll evaluate x minus y, so I can write cos of twice of 2 pi f 2 delta t, and similarly if I'll evaluate x plus y, I will get this expression, right. So this is cos of x plus y, cos of cos of x minus y minus cos of x plus y. So divided by 2 obviously, right? Divided by 2. So this will give us this expression cos of 2 pi f 2 delta t minus cos of 2 pi f 2 k delta t plus 2 delta t plus 2 theta, right? Okay, now hence we can now substitute the evaluated values from last slide, that vk plus 1 square minus vk into vk plus 2 will be equal to a square into 1 minus cos of twice whatever we have evaluated minus of cos of 2 pi f 2 delta t minus cos of 2 pi f 2 k delta t plus 2 delta t plus 2 theta, right? So now if we'll just expand these expressions of cosine terms, just expanding these cosine terms, I can find a square, final expression I will find a square into 1 minus cos of 2 pi f 2 delta t by 2, right? Hence now using the trigonometric identity of cos 2x I can write simply twice of cos x square minus cos square x minus 1, and just simplifying it I will get this expression, just substituting the value of x here, right? X is here, nothing but here, that is 2 pi f 2 delta t. So just substituting here I will find final expression as this a square twice of this. So now substituting here I will find that vk plus 1 square minus vk into vk plus 2 will be equal to a square sine of 2 pi f delta t whole square, right? Now from this expression I can write a of sine 2 pi f delta t will be equal to vk plus 1 square minus vk into vk plus 2 square root. Okay, and from this equation I can find the value of a, that is the amplitude of the signal. So that is a equal to vk plus 1 square minus vk into vk plus 2 square root divided by sine of 2 pi f delta t. So this will give me the expression for the amplitude of the signal, right? Similarly, if we will go for the phase angle calculation, so simply I can estimate this phase angle just from one equation, from one sample, that is because already I know the frequency, already I know already I know a amplitude and frequency, so only we need to find theta. So therefore from this expression I can find theta. So theta will be nothing but it will be sine inverse bk by a minus 2 pi f k delta t. So already we know a, this is amplitude, and already we estimated frequency, and hence very easily we can find the theta, that is the phase angle of the signal. So now our phasor information is complete. We found frequency, then amplitude, then theta. So all these after getting these informations, we can again use these informations for overcurrent relay, similar to whatever I have shown for Mann Morrison algorithm. The same algorithm can be, same way of implementation can be used for overcurrent relay, for directional overcurrent relay and distance relay. So this is the summary of 3 sample technique. So the signal we considered here is V equal to Vm sin omega t plus theta, and we need to collect 3 samples, Vk, Vk plus 1 and Vk plus 2, and these are the expressions for the samples. And from that first we need to estimate the frequency, then after that we estimated the amplitude. The frequency expression we got is 1 by 2 pi delta t cos inverse Vk plus 2 by 2 Vk plus 1, and the amplitude, the expression of amplitude we got is Vk plus 1 square minus Vk into Vk plus 2 square root by sine of 2 pi f delta t, right? And similarly after that we found the expression for theta, that is theta k is equal to sine inverse Vk by a minus 2 pi f k delta t, where f and A are known quantities from the above expressions, right? Okay, so now we is a summary, and obviously we'll stop here, and next class we'll continue with few other algorithms. So we'll stop here. Thank you very much for your kind attention. Thanks a lot.